Hi everyone, my name is Bhanu Tej. I am studying in Institute of Aeronautical Engineering. I am studying in Data Science A section. My roll number is 17. I am going to discuss about non-standard electrical networks and the resurrection of Kirchhoff's law. Kirchhoff's law. Laws Kirchhoff. The laws of Kirchhoff are the two equations that address conservation of energy and charge with reference to electrical circuits. They are very important in the analysis of closed and complex electrical circuits such as bridge or T networks, in which calculating voltages or currents circulating within the circuit becomes difficult using Ohm's law alone. Kirchhoff's law is used to make the solving of current easy and find out the current with easy process. Kirchhoff's law of current and voltage. Kirchhoff's current law, KCL. The first law of Kirchhoff is called Kirchhoff's current law. It states that the total current or charge entering a junction or node is exactly equal to the current leaving the node, as no charge is lost within the node. It can also be stated as the sum of the currents in the network of conductors meeting at a node is equal to 0. That is, current entering the node is equal to current leaving the node. The node is also called as junction. The junction of two or more branches is called as node. I1, I2, I3. These currents are entering the node, and I5 and I4 are leaving the node. By the statement, the current entering the node is equal to the current leaving the node. That is, I1 plus I2 plus I3 is equals to I4 plus I5. That is Kirchhoff's first law. That is, I1 plus I2 plus I3 is equal to minus of I4 plus of minus I5 is equal to 0. That is, all the currents in a junction is equal to 0. So all the sum of the currents in a junction is equal to 0. Kirchhoff's voltage law, that is the Kirchhoff's second law, KVL. The Kirchhoff's second law is Kirchhoff's law of Kirchhoff voltage law. It states that in many closed loop networks, the sum of the EMF values in a closed loop is equal to the sum of the potential drops in that loop. In other words, it can also be said as the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is equal to 0. That is, the total voltage around the loop is equal to the voltage drops within the same loop. That is, the source voltage is equal to the sum of load voltages. That is, the voltage of the resistors, that is V1 and V2. The loop direction, we can assign the signs of the voltage, source voltage and load voltages. That is, minus V1 plus V1 minus V plus V1 plus V2 is equal to 0. This is the equation of KVL, Kirchhoff's voltage law. Applications of Kirchhoff's voltage laws. Kirchhoff's laws. They can be used to analyze any electrical circuit, computation of currents and voltages of complex circuits. Advantages of Kirchhoff's law. Calculation of unknown currents can be and voltages is easy. You can calculate the currents and voltages in a loop in easy manner, or it takes less time to calculate the current and voltages. Simplification and analysis of a complex closed loop circuits becomes manageable. We can do the problem or the circuit. We can find the currents and voltages in less time, and we can do the experiment in an easy manner. Limitations of Kirchhoff's law. The limitation of Kirchhoff's law, both laws, is that it works under the assumption that there is no fluctuating magnetic field in the closed loop. Electric fields and EMF could be induced, which causes the Kirchhoff's loop rule to break in presence of variable magnetic field. This is why we can't take the fluctuating magnetic field in the closed loop. When the Kirchhoff's circuit is exposed to the magnetic field, then the EMF is induced into the magnetic field, which breaks the Kirchhoff's loop rule. Electrical networks. An electrical network is an interconnection of electrical components. Examples: battery, resistors, inductors, capacitors, switches, transistors are a model of such an interconnection consisting of electrical elements. Example: voltage sources, current sources, resistance, inductance, capacitance. An electrical circuit is a network consisting of a closed loop giving a return path of the current. Linear electrical networks, a special type consisting of sources, voltage or current. The linear lumped elements, resistors, capacitors, inductors. The linear distributed elements, transmission lines, have the property that signals are linearly superimposable. They are thus more easily analyzed using powerful frequency domain methods such as Laplace transformers to determine DC response, AC response, and transient response. The electrical networks are divided into two: active element and passive elements. Active elements are capable of delivering energy to the external devices. Passive elements are capable of only receiving energy or power. Active elements are divided into two: voltage source and current source. Voltage source is represented by this symbol and current source is represented by this symbol. In passive elements are divided into three: resistor, capacitor, and inductor. Resistor is the symbol of resistor is this, and the symbol of capacitor is this, and the symbol of inductor is this. Now we are going to learn about non-standard electrical networks and resurrection of Kirchhoff's law. Introduction. Kirchhoff's law fails to hold in general for infinite electrical networks. Standard calculus is simply incapable of resolving this paradox because it cannot provide the infinitesimals and more generally the hyperial currents and voltages that such networks often require. However, non-standard analysis can do precisely this. The idea of non-standard electrical network is used to re-establish Kirchhoff's law for a fairly broad class of infinite electrical networks. Not only conventionally finite but also many transfinite electrical networks will have non-standard representations. One consequence of our introduction of non-standard networks will be the re-establishment of Kirchhoff's law as innovate rules for certain infinite networks. The kind of non-standard network we shall consider is a finite interconnection of one ports having non-standard parameters. We shall show that certain one ports which are internally finite have non-standard descriptions. Conclusions. We Therwin may be able to partition into finitely many one ports and analyze the interior circuitry of each one port by applying Kirchhoff's law and Ohm's law to a sequence of finite networks arising from opens or shorts in order to find hyperial solutions to that circuitry. In particular, we may obtain a hyperial Therwin or Norton representation of each one port. As its port terminals, then a non-standard nodal or fundamental loop analysis applied to the finite circuit of Hyperion 1 ports will yield the Hyperion port voltages and port currents at all the 1 ports of partition of. These in turn determine all the Hyperion currents and voltages within the 1 ports, and latter will satisfy non-standard versions of Kirchhoff's law of at all finite and infinite ordinary nodes around all finite and transfinite loops. Result: it appears that non-standard analysis is overly delicate, for it requires more specifications than it is provided by just the graph and the element values of the infinite network. The constructive approach of non-standard analysis does resolve the paradoxes about Kirchhoff's law, at least for certain infinite networks, but it may also produce many different non-standard images for a given infinite network. The circuit theorist is free to choose among them. Comment. Let us comment on what has not been achieved. The sentences of symbolic logic are the finite length and therefore cannot encompass an infinity of terms. As a result, assertions concerning an infinity of real terms cannot in general but transferred into the Hyperion realm. However, not all transfinite networks have been encompassed. How to proceed when every finite partitioning of the network results in at least one port having both infinite nodes and transfinite loops, but no assurance of an essentially spanning tree, remains an open problem. Thank you.